Welcome to your Chapter 3 AP Statistics video. Today, we're going to talk about displaying and describing categorical data. All right, remember categorical data is are observations where each observation falls into one of several cases for a category. So we could be looking at the color of cars in the parking lot. And so we would have silver, silver, black, white, silver, blue, black. Those would all be observations. So how would we make it where somebody could really visualize the pattern and the variation that's going on? Well, there's 3 rules that you need to remember, and they're all the same, and it's to make a picture. You're going to reveal things that aren't obvious in the raw data. A whole list of colors would be hard to actually analyze at all. Important features and patterns are going to show up. And best of all, you can then turn around and tell others. You can communicate what the data are telling. Okay. So we compile data by counting the number of values in each category of interest in each of those categories and make a frequency table. They're a good way to summarize the data before we try to make a picture. Okay, so here we have data from the Titanic. And so there were 325 first class tickets, 285 second class tickets sold, so 285 second class, if you will, patrons, and then 706 in third class, and 885 people in the crew. All right. So you can also make a relative frequency table, but you give the percentage of the group that falls into each category instead of the count. So in our Titanic data, almost 15% were in first class, about 13% in second, 32% in third, and 40% of all the people on the Titanic were part of the crew. All right. So how to make a good picture of what's going on. You might think that this is a good way to show the Titanic data, but if you remember the area principle, it's not. Because what they are doing is they are using the magnitude in both the horizontal direction and the vertical direction. And so you think the difference, say, between the crew and the first number of first class patrons is larger than it actually is. So what should happen is that whatever you're looking at on your graph should correspond to the area principle, where everything is in the correct proportion, so that your brain is able to understand the relationships just simply by looking at them. So the way that we do that is by making sure that the difference between each category is in one direction only. So usually what we do if we're doing a bar chart, which we're going to talk about, is we fix the horizontal length of each rectangle of each bar, and then we let the height of each bar show the difference between the different categories. So here we've got a bar chart. It's very easy to see that there were quite a few, there were a little more first class passengers than there were second class, a whole lot more third class, almost the same as first plus second. And then the crew was by far the largest group. And the nice thing is it stays true to the area principle. It's not cool to look at like the ships, but it's honest. Relative frequency bar chart is where you have the percentages or relative proportion, relative frequency on the vertical. And you notice that the shape is the same. It's been scaled to percent. Many times you can choose between whether you're going to use counts or relative frequencies. And the only thing you need to make note of is if you are comparing two groups, especially if there's a different total number, you want to use the relative frequency bar charts to compare them so that you have a common scale of per 100. All right, pie charts are a great way to show the parts of a whole. Okay, so here we've got the whole, everybody that was on the Titanic, and then we have discrete categories where there's no overlap and where everybody falls into one of the categories. So we make a bar chart, and the way that you make it follow the area principle is that the size of the segment that you have for each category is proportional to or equivalent to the proportion of the total number that you're working with. Okay, sometimes the best way to summarize or another way to summarize that's helpful in analysis is by making a contingency table or a two-way table. Contingency and two-way table means the same thing. So they allow us to look at two categorical variables together. It shows you how the individuals are distributed along each variable and contingent on the value of the other variable. For example, we can examine the class of ticket and whether or not a person survived the Titanic. Okay, there are a couple of different kinds of distributions that we're interested in. The first one is the marginal distribution, and that's where you isolate one of the variables and you look at the totals in each of the categories of that variable. So for instance, the marginal distribution of survival is found here, where you add up all of the individuals who survived. And so there were 711, and then you add up the count of all the individuals who died, and there was 1,490. And then to get the table total, it is 2,201. Okay. We can do the same thing for class. So down here along the horizontal, you will see that there were 325 people with a first class ticket, 285 with a second class ticket, 706 with a third class ticket, and 885 crew members, again for the same total of 2,201. What you find in the table are the counts of people that meet two different criteria, or who fall into a particular combination of values for the two variables. So right here, there were 673 members of the crew who died. Okay, there were 203 first class ticket holders who were alive. Okay, you can see where it's broken down by each category. Okay. Many times we're interested in a conditional distribution, and that's going to be where we narrow our focus. Okay, so instead of looking at all 2,201, we might look at all 711 people who were alive, all 1,490 who died, and look at how the percentages fall across the different classes of either ticket or membership in the crew. In both scenarios. We could also do the same thing going by class. Okay, so this is the conditional distribution of ticket class. Okay, so that's what's distributed here, conditional on having survived. So we want to know what percent of the people who lived had a first class ticket, second class ticket, third class ticket, and were crew members. So here's our counts, and below you'll see our percents. So for instance, for the alive first class ticket holders, you do 203 divided by 711 times 100%, and you get 28.6%. And then 16.6%, 25%, and 29.8%. And we can do the same thing among those who did not survive. So you can see there's a difference here. There were 28.6% of the survivors were first-class ticket holders, and only 8.2% of the dead were first-class ticket holders. 11.2% were second-class ticket holders. 35.4% were third-class ticket holders, and 45.2% were crew members. Okay, so one question that would be relevant is whether or not people had an equally likely chance of being among the living or among the dead, no matter what class ticket they had or if they were members of the crew. So if we compare these pie charts of the people who survived the Titanic and the people who died from the Titanic, we can get an idea of whether or not the chances were the same for somebody, say, in the first class ticket to end up alive or dead. And if we look here, among the living, there's a much bigger portion for the first class ticket holders, and among the dead, there's a much smaller. So in the second class, there's larger in alive, smaller in dead. But look, the trend shifts. There is fewer percentage-wise of the third-class ticket holders who were alive, and a larger percentage of the dead who were third-class ticket holders. And then for the crew members, the difference is even larger. So we see that the distribution of class for the survivors is different from that of the non-survivors. So this leads us to believe that class and survival are associated. They are not independent. The variables would be considered independent when the distribution of one variable in the contingency table is the same for all categories of the other variable. So what it's saying is that the two pie charts would have to look alike. It's not saying that each category would have the same size piece of the pie chart. It's just that they would match. Okay, and that makes sense because you had different numbers of people in each of the ticket classes and in the crew, so you would expect to have different proportions in the living and the dead. If they were independent, then we could also make the pie chart. We could go back to the pie chart of just class of ticket holder and crew. This pie chart would look just like the two that we had here if they were independent. Because they don't look alike, we have evidence that they're not independent. Now, in statistics, when you say two things are dependent, that means something specific that falls outside the scope of this course. And so we just say that they're not independent, okay? So a segmented bar chart is essentially kind of the same thing as a pie chart, but just in a different form. And so here we have a segmented bar chart with the group of people who are alive and the group of people who are dead. And then what you do is you start with one of the categories. So they started with crew and said, okay, 30% of the living were in the crew. And then they took the percent of the living who were third-class ticket holders and added that. And then they added the percent of the living who were second-class ticket holders. And then finally, they added the percent of the living who were first-class ticket holders, and it all adds up to 100%. And then we do the same thing with the distribution among the dead. And certainly you can see here, sometimes it's even easier to see in a graph like this that there is definitely a difference in the distribution. We're going to look at another type of graph later that is similar to this, but then goes back and adjusts actually for the size of the number of people who are alive and the number of people who are dead, but we will save that for another day. Okay, so we know now that we can summarize categorical data by making the frequency table or a relative frequency table, so that we know how many cases or the percent of the cases that fall into each category. We can display the distribution in a bar chart or pie chart or the segmented bar chart. And we can examine two-way tables called contingency tables for both marginal and or conditional distributions of the variables. Okay, so let's look at a couple of examples. In this example, we're going to look at a December 2000 report from the Census Bureau, and it has listed the levels of education attainment for Americans over 65. Create an appropriate display for these data and write a sentence or two that might appear in a newspaper article about the report. So we have the counts here, and it's nice to have the counts, but honestly, to be able to have an idea of, well, how does 9,945 compare to 3,133 in this population? It's hard to get that from the counts, so we're going to do the relative frequency distribution, and so that means we're going to take the class count and divide by the grand total and then multiply by 100. And so we're going to make a relative frequency table just to scratch work, and then we'll make our display, which is what the problem is actually asking for. All right, so I want to find the relative frequency, so I add up and get a grand total of 32,620 people were in this sample. And so the percent or relative frequency who had no high school diploma was 9,945 divided by the 32,620 and multiplied by 100% to get 30.5%. So I did the same thing, took the count for the category and divided it by the total count, multiplied by 100%, and got the other values. All right, so I decided it would be really hard to make a good pie chart that had this many categories. So I'm going to make a relative frequency bar chart. We're not comparing two samples, and so making a segmented bar chart really wouldn't be your best choice here. Your best choice here is just to make a good old relative frequency bar chart. So to do that, I have each of my categories, and I have percent of U.S. seniors. Now, mind you, I probably should have put, senior citizens or seniors, and then parenthetically people over 65, so that people weren't confused with, well, seniors in high school, seniors in college, but it says seniors. So here we've got the percent. Notice that we have a good label up here, a good title. Now, on your graphs, I am going to want you to tell me if this is percent, and you can just use the percent sign, or if it's a count. I do think that's important. You can either do a key like is over here, or you can label the vertical axis. It's also good to remind people what we're looking at here, and put that this is the highest level of education attained. So we can look at this and see that the largest percentage, not a majority, it's a plurality, it's the largest percentage, but it's not over 50%, fell into the high school graduate, no college. And next was the no high school diploma, and then some college, no degree. There's a little bump up in 4-year degree, and then 2-year master's and doctoral or professional degree. So we want to describe this. And so if I were going to summarize this in a newspaper, I might put something along the lines of the majority of people surveyed either did not graduate from high school or graduated from high school but did not attend college. Fewer than 20% received 2-year degrees or higher. So I summarized grouping the first two categories together, and then I summarized lumping the last several categories together. All right. So here on the next example, we are going to look at a contingency table, a two-way table, where students were asked to describe whether they consider themselves liberal, moderate, or conservative, and their genders were recorded as well. And so 192 students participated in the survey, and among them, 85 were liberal, 80 were moderate, 27 were conservative, 77 were female, and 115 were male. So let's analyze this a little further. The first question we're going to look at is what percentage of the class are males? All right, so this is the percentage of the class. So our denominator is going to be 192, and we want to know the percent that are males, so our numerator will be 115, and then we'll multiply by 100% and get 59.9%. What percent of the class is conservative? Same concept. Our denominator is still going to be 192 because we're interested in the whole class, and we want to know what percent of that class is conservative. So the 27 is our numerator, and so we have 27 over 192 times 100% is 14.1%. Okay, so now we're going to shift to looking at the men only, the males only. What percent of the males, so our new denominator is going to be 115, are conservative? So 21 out of 115, okay? And then times 100 gives me 18.3%. So we are restricting our sample or our population, in this case, however you want to think of it, to the 115 males. And then what we're interested in is the percentage of those 115 males who are conservative. So it's just those 21 conservative males in our numerator. What percentage or what percent of the students are male conservatives? Okay, so this is going back looking at all 192 students, and we're still in our numerator going to have the male conservatives. So it's going to be 21 out of 192 times 100% is 10.9%. Okay, this is going to be kind of an interesting problem, and something kind of cool happens that maybe you wouldn't expect. A company must decide which of two delivery services they will contract with. During a recent trial period, they shipped numerous packages with each service and kept track of how often deliveries did not arrive on time. Here are the data. Okay, so if you look at Pack Rats, they did 400 regular deliveries and had 12 late packages. They did 100 overnight deliveries, and they had 16 that were late. Boxes R Us had 100 regular deliveries, and they had 2 late packages and 400 overnight deliveries, and there were 28 that were late. So we're going to compare the two services' overall percentage of late deliveries. Okay. So we're going to add, they had 12 plus 16. You can see 12 plus 16 divided by 400 plus 100. Okay, so they had 500 total packages, 28 total that were late, and we're going to multiply that by 100%, and we get 5.6%. Boxes R Us had a total of 500, and their two values of late packages were 2 and 28, so we get 30 over 500 times 100% is 6%. All right. Based on the results in Part A, the company has decided to hire Pack Rats, right? Because it's 5.6 and the other one is 6%. Do you agree they deliver on time more often? Why or why not be specific? Let's look at something. If both groups had the same number of regular deliveries, okay, 400 versus 100, and the same number of overnight deliveries, okay, if either both groups had 100 or both groups had 400, where those two were equal, then there would be no other consideration really that for us to look at. Also, if regular packages were just as likely as overnight packages to be late, then this difference in proportion of regular versus proportion of overnight that the two services are experiencing, if there was no difference in percentage late packages among regular and among overnight, then there wouldn't be anything else to consider either. But if you look, pack rats had 12 regular and 16 overnight. Boxes R Us only had 2 out of their 100 regular and 28 out of 400 overnight. Okay, so the question is, does the fact that pack rats had so many more regular deliveries than overnight deliveries versus Boxes R Us, does that do anything to make us go, oh, wait, let's look and break this data down? Well, let's go ahead and do that. All right, if you break the data down and do the conditional distribution for the different types of service, if you look among the regular packages, pack rats had 12 out of 400 that were late. So 12 divided by 400 times 100% is 3%. For the overnight packages, 16 out of the 100 that they were sent were late. So that gives us 16%. If you look at Boxes R Us, only 2% of their regular were late and only 7% of their overnight were late. It reverses who did better if you break it down by category. And the reason for that is because pack rats has a much lower rate of the late packages overall. It's because they had a much lower percentage of overnight packages. 20% of all their packages were overnight versus 80% for Boxes R Us. So actually, when the data are what we call disaggregated, okay, broken down according to categories of an important variable, then we see that there is actually a reversal of what we first thought was the better company. This is an example of Simpson's paradox, when the distribution of overall results indicate one pattern, but the distribution of conditional results indicate the opposite pattern. The trick is, though, usually somebody has to stop and notice this difference. Okay, somebody has to go, oh, wait a minute. The reason Boxes R Us overall has the higher percentage of late packages in general is because they have a higher percentage of overnight packages, which overnight delivery is harder to do on time than just a regular, 2 or 3 day delivery. Okay, guys, go ahead and try the problems to try on your own, and I will see you in class. Have a good day.